Okay, let's start. So, previous week, if we recall, we have done direct sequence spread spectrum. So, first we discussed the motivation of why we use spread spectrum in modern communications, and along with that, we explained the mechanism of direct sequence spread spectrum, and then we solved some problems regarding that direct sequence spread spectrum. So, spread spectrum, as you have got by now, that it is of two kinds mainly. There are other kinds also, but two kinds that are used in the state of art. That is, one is DSSS that we have done today, in the yester week, and another is FHSS. So FHSS is frequency hopping spread spectrum. So here the free beat frequency hopping, time hopping, or whatever hopping spread spectrum, everything functionally is of one essence, that it has a pseudo random sequence and something. It can be frequency, it can be time slot. I am sorry, sir, but we are not actually supposed to divulge our communication details. So, whatever doubts you have to give in the Google forum, and I will only be seeing that as I am the TA. So, I will only be seeing that, and I will be answering you accordingly. But due to our policy, we cannot divulge our personal contact details. Neither can we ask of yours. Okay. So that I hope that answers your question. So yeah. So the basic philosophy of spread spectrum is that there is a pseudo random sequence, not exactly random. Because if something is purely random, then it is generated at the transmitter and the receiver has no clue. The receiver has no clue, because if it is purely random, it cannot regenerate something that is purely random. So it is pseudo random. It is random to someone who is outside of the system and deterministic to someone who is inside the system. That is the pseudo random system. So there is a pseudo random system which is generating a pseudo random sequence in transmitter and regenerating that same pseudo random sequence in the receiver, and according to that specific pseudo random sequence, some parameter, be it the data itself, as in DS3, in DSSS or DS3, the data itself is getting manipulated by the pseudo random code. Whereas in frequency hopping spread spectrum, the frequency of the signal that we are sending, the carrier frequency, the tone of the signal is changing with the PN sequence. In time hopping spectrum, your time slots are changing according to your PN sequence. So all spread spectra have this core logic. Now this is where the similarities end and the differences begin. A direct sequence spread spectrum just involves a XOR. Basically, you are a XOR, and then you do a XOR to generate the of a shift register to generate the pseudo random sequence, and then you are doing a dot product on that. Can full screen is my screen not visible, guys? Geeks for geeks, can you see? My full screen should be visible. Okay, yeah, yeah. And right now I am not saying anything from the screen anyways. So yeah, so now let's focus on the screen. If the diagram is visible to you, you can see that what this frequency hopping spectrum does. So there is something which is the data that is getting modulated using frequency shift keying. Now what is frequency shift keying? Frequency shift keying means that say, like, let's open some writing. Yeah. So in frequency shift key, what is happening is that your data is getting modulated by a tone, and that tone value depends on the data. So the tone of the carrier depends on the data. So it can be cos 2 pi f1t if data equal to 0, and cos 2 pi f2t when data equal to 1. where of course f1 is not equal to f2. So this is FSK. Now this FSK has only two distinct tones. So if there is a serial binary data, it will modulate in two tones. Now these two tones might not be sufficient for spread spectrum. What spread spectrum does is it has a pseudo random code generator, like we have said. What is this pseudo random code generator? It is basically a shift register with a XOR gate that you can find in any textbook, how to generate PN sequence. So it is a shift register with a XOR gate. Now this shift register with a XOR gate, this code is passed to frequency synthesizer. Frequency synthesizer has a set of frequencies it can generate. So what frequency synthesizer has is basically, like, say there is a 4-digit PN sequence. Okay, 0000, like the PN sequence is 4-bit PN sequence. Of course the PN sequence is longer, but for demonstration we should take a very small bit. So 00 0 0 0 0 0 1, like that, 0 0 1 0. I am not writing everything. And then finally what you will have is 1 1 1 1. And how many such? 16 such. Okay, now what this frequency synthesizer will do is it will map something like f a, let's say, because f1 I have already used, fb, these are all different frequencies, fc. So whatever the PN sequence bit is, PN sequence vector is, it will generate a frequency tone according to that bit pattern. So now you have FA. So let's say you wanted to transmit 0 1 0. Okay. Okay, 4-bit PN sequence is still a bit large. So what we should do is we should take only 2-bit PN sequence. Okay, that will be much more easier to demonstrate for you. 0 0 0 1 1 0 and 1 1. Now, so these are FAFC, FAFB, FCMT. These are fine. So you want to set data 0 1 0. Data is 0 1 0. So your FSK, what will it give? Tones. First it will transmit a F1 tone, then it will transmit a F2 tone, then it will transmit a F1 tone. Now if you see the block diagram here, you will see there is a mixer. So this F1 tone is getting mixed with what tone? This F tone, FA tone or FB tone, this frequency synthesizer tone. So mixer, what will it do? It will basically, mixer is what? It is de facto a multiplier. So it will, so what will it do? It will multiply cos, say your PN sequence for this particular first bit, say bit 0. Okay, bit 0 means the value of bit 0, or bit 1, let's say bit 1. What is the value of bit 1? The data is 0 1 0. So what is the value of bit 1? 0, right? The first bit 0. So tone, FSK tone, F1. Are you following this? FSK tone is F1. And so the mixer, which is de facto a multiplier, the PN sequence that will be generated for this, the PN sequence for transmitting these bits, bit 0, say that is 0 1. So what is the synthesizer tone? Synthesizer tone is FB. So mixer will give a de facto, mixer is a de facto multiplier. So it is cos 2 pi F1t times cos 2 pi FBT. Now, as you know, this will give you two tones. One is FA plus F1, another is FB plus sorry, FA, not FA, FA, not FA, FB. One is FB plus F1 and another is FB minus F1. Now let's check what they are doing. So yeah, so the frequency synthesizer, now you have to of course transmit a particular frequency, so one of these tones. So there is a band pass filter which will of course filter out one of these tones and you then transmit. Okay, so let's say this one is filtered out, so this one is filtered. So what will you ultimately transmit? This. Now when it comes to the receiver cannot generate the F1 tone if it does not know the PN sequence. And it will only know the PN sequence if it can generate the PN sequence at its end. And it can generate the PN sequence at its end if it knows the key to generating the PN sequence. Or else it has to brute force, which is not feasible for a long length of PN sequence. So if it cannot generate FB, not F1, FB, it cannot generate FB, then it cannot of course demodulate perfectly. So now we will go to the specificities of FHSS, more like mathematical side. So yeah, is the principle of frequency hopping spread spectrum clear up to now? Does anyone have any question on FHSS? Okay, apparently not. So let's now go to the mathematical part. 1 minute. Yeah. So I'll just open the textbook. For the mathematics. So yeah, I think I have suggested this textbook already. So you can look into this. This is a classic textbook for spread spectrum. So yeah. Okay, now if the data, here you see, there is a frequency hopping system. Like I said, there is data goes through modulator, and code generator gives a particular tone for the frequency synthesizer, and we finally arrive at the, by mixing them, we arrive at the frequency hopped signal. Now, this textbook of course further generalizes. We have said FSK, but it can be PSK also. So instead it is some angle modulation phi t. So this phi t can be FSK, can be PSK. So that modulation part will be there. Plus there is an additional 2 pi FJT where J is the carrier frequency for this hop. So if the data modulation is some form of angle modulation phi t, then received signal for ith hop is St is equal to root 2s, which is the signal strength basically, cos 2 pi FJT. Now cos 2 pi FJT means it is cos 2 pi FJT. This part comes from the frequency hopping, and phi t, this part comes from the angle modulation, and phi I is the, whatever the initial epoch is, or the, okay, it is not the initial epoch, it is the random phase angle for the ith hop. So this is like the angle phase, whatever is remaining epoch. So the frequency hopping pattern produced by the receiver synthesizer is synchronized with the pattern produced by the transmitter, but is offset by a fixed intermediate frequency. Why is it offset by a fixed intermediate frequency? Because there is some this angle modulation term. So this angle modulation term, of course, the hopping pattern pertains to the FJ. The phi t is independent of hopping. That is just your plane modulation. So it has to offset that. So it has to offset that frequency and then generate. It cannot just match the direct received signal frequency. Okay, is that understood? So the mixing, then it is finally mixed. The mixing operation removes the frequency hopping pattern from the received signal and is called, hence called dehopping. The mixer output is applied to a bandpass filter that is, well, then you just filter out the frequency and you finally get your dehopped signal. Okay. So, wait. Yeah. Now we go to the dehopping. This mechanism scheme. So the whatever the hopped signal that has been generated at the transmitter, that is only recovered here. Of course, we are not considering all those amplifiers and all that passband technology. We are not concerned with. We are strictly dealing with baseband technology. So here and then there is a code generator and again a frequency synthesizer at the receiver. Now this code generator frequency synthesizer, of course the code generator will share the key, but still it has to be synchronized at the exact time the frequencies are getting, because you see each bits, how many bits are, like say there is 1 Mbps. 1 Mbps means each microsecond there is a bit transmitted. Okay, so 1 Mbps means each microsecond there is one bit transmitted. Now in that microsecond level we need synchronization. So that synchronization system is not specified here, but the synchronization system is basically to keep these two in lock. So it is, now what device do we use to keep two kinds of frequencies in lock with each other, to keep two kinds of frequencies in lockstep with each other? What is the exact name of that device? We use phase lock loops or PLLs. So synchronization system, of course, is not described here in detail, but it involves PLLs, some kind of PLLs. So it has to synchronize this signal, the whatever we have dehopped, with the code generator. Okay, so there is a synchronization between the transmitted signal and the received signal. So this is there, and then finally demodulate and output. Now let's go to the questions, and then whatever, since we have covered the exact basics of the spread spectrum, now we will go to the questions, and for each question of course there will be concepts involved which we have not covered yet, then we will cover them one by one. So yeah. Um, okay. Now the first question is, a frequency hopping system with 6-stage linear feedback shift register is generating the maximal length sequence. Each state of the register dictates a new center frequency within the hopping bandwidth. The desired hopping bandwidth is 81.9. The chip clock rate is 10 kHz. Assume MRE FSK modulation and data rate is 4 kHz. So of course this is a whole lot, and to the uninitiated it might sound like Hebrew. So let me decode. So there is a frequency hopping system with a 6-stage linear feedback shift register. That means the PN sequence will have 6 bits. I'm sorry. Now each state of the register dictates a new center frequency. So 6 stage means how many states are there? 2 to the power 6, which means 64. So there are 64 different tones. Each state of the register dictates a new center frequency within the hopping bandwidth. So of course there is, the tone changes, but the bandwidth has to be within the hopping bandwidth. We cannot have infinite, we do not have the purchase of the infinite bandwidth. There is a restricted band in which we have to transmit, and the hopping must happen between that restricted band, and each of the hops should only take that much band so that it does not interfere with another hop. Okay, so that is there. But of course, if you transmit it directly without any hopping, you will need 64 times less bandwidth. So that is the trade-off of spread spectrum, that you get secrecy, you get privacy, but you spend bandwidth. But there is a trade-off, like what to say, counter argument to that trade-off, that we can accommodate more users. Why? Because here also we can simultaneously using the same mechanism as DS3, that different port transmitter receiver pairs will have different port generation keys. So at the same time, a particular tone may be mapped to some data in for one user, may be mapped to another data for another user. So the tone sequence, so there are, say, 5 users are there, the 5 users are using the same tones. So this one has 64 tones, so the 5 users are using the same 64 tones, but the pattern in which they are using, that is unique, and that is shared only between the transmitter and the receiver, and the other 4 users who are eavesdropper for this communication, they cannot decode the hopping pattern. So whether it goes FAFB FCFB or it goes FDFA FBFC, what is that hopping pattern, that they cannot decode. Okay, so sometimes FA is getting mixed, sometimes then FB is getting mixed, then again FB is getting mixed. This pattern, this is why it is hopping. If first it goes to FA, then it is FB, then it is FA, then again FC. So it is hopping around. Okay. One side note: this spread spectrum, this frequency hopping spread spectrum technology was proposed by Hedy Lamarr, who was a actress of yesteryear Hollywood. So yeah, that is a one interesting side note. So this technology was proposed by an Hollywood actress, which is very rare to and unique combination. So yeah, let's not go that way. So the desired hopping bandwidth is 81.9, and the bandwidth is hopping bandwidth is given to be 81.9, means the bandwidth in which the spread spectrum frequency dancing, the frequency is dancing between 81.9. So you have to generate all those 64 tones in this 81.9. It cannot go beyond that. And the chip clock rate is 10 kilohertz. Assume MRE FSK modulation, and data rate is 4 kbps. So minimum step size between center frequency. Now, of course, we have interpreted the question, but we still don't know what is how to solve this, because we have, of course, not seen the formula and how the modulation is done. So for that, we will go to the solution. Okay. Yeah. Well, let's not go directly to the solution. First, let's talk about MREFSK. Yeah. 1 minute. I have a particular presentation, but I need to open it. Just give me 1 minute. I need to retrieve a PDF presentation. It is there, but I need to bring it to my computer. I will stop sharing the screen for 1 minute. Okay, let's share it again. Where is my screen? Yeah, yeah. So we have kept that problem in mind, MREFSK, but I would like to add some more about FHSS before we go to that problem, specific problem. So yeah, okay. So this is the MREFSK frequency hopping that we know. Acha, this is what I wanted to cover. That depending on this rate of frequency hopping, the FH frequency hopping MFSK, MRE frequency shift keying. So FHMSK, MFSK system are classified as slow frequency hopping or fast frequency hopping. In slow frequency hopping, symbol rate of MFSK is integer multiple of hop rate. That is, in each frequency hop, several symbols are transmitted. Therefore, each frequency hop has several symbols. In fast frequency hopping, the hopping rate is the integer multiple of symbol rate of MFSK. That is, during transmission of one symbol, several hops are made. Therefore, each symbol transmission has several frequency hops. So, what I mean to say is, in the first example I have shown, shown you that for each bit you are hopping one. So, like if it is say 8 FSK, okay, 8 FSK means 3 bits make one symbol. So, if 3 bits make one symbol, that means that and each bit has one hop. 3 bits make one symbol and each bit has one hop. So so that in transmitting each symbol, total 3 hops are made. Refer to my example here. I think confusing you. So refer to my example here. So 0 1 0, only 3 bits, and for that 3 bits I am saying each bit you make one hop. So 3 bits means 3 hops. Now 3 hops mean, and the data rate, the symbol rate is only 1. So say this whole process takes 1 second. So what is the hop rate? Hop rate is 3 hops per second. So 3 times tone is changing per second. Whereas your symbol rate is 1 symbol per second, because after you have transmitted this 0 1 0, say this is 1 symbol. So this is 1 symbol for 8 PSK or 8 FSK. Okay. So this is just 1 symbol. So hopping rate. So is this a fast hopping or a slow hopping? So this is a fast hopping because each symbol needs multiple hops to transfer. Okay. So for FHSS, the chip rate is maximum of the symbol rate and the hopping rate. Now, what is the chip? Chip is basically the spread spectrum PN sequence. So, if you are making so for FHSS, maximum of symbol rate and hopping rate. So, how to understand this? If your hopping rate is more, so you are generating 3 hops, and if your symbol rate is more, so in one hop you are generating 3 symbols. Okay, so in one hop you are generating 3 symbols means each chip represents each chip represents 3 symbols. So your chip rate is your, basically, for each if you are making say 3 hops for one symbol. If you are making 3 hops for one symbol, that is fast FHSS, then you are making 3 hops for one symbol. So in that case, each hop is generating one chip. So you are generating 3 chips. So your chip rate is 3. Say you are doing it in unit time, 1 second. So your chip rate is 3. Whereas in slow FHSS, in one hop you are generating 3 symbols. Now you cannot say one chip is equal to one symbol, 3 symbols, because those 3 symbols might be for 3 different people. Understood? What is a chip? In the direct sequence spread spectrum, you will see that, say one user has a code +1 -1 +1 -1 -1. and another has -1 +1 -1 +1. So each user has a different chip. Here also each user has a different tone pattern. F1, one might have F1, F2, F3, F4, one might have F4, F3, F1, F2, like that. So if you're in slow FHSS, you are just transmitting three symbols in one chip, one hop, but you cannot say that you are transmitting three chips. One chip. You are transmitting three chips. You cannot say you are transmitting only one chip, because those three symbols are meant for three different people. So chip rate is basically where is the maximum of symbol rate and hop rate. So if you are having multiple hops in one symbol, then it is hop rate, and if you are having multiple symbols in one hop, then it is the symbol rate. That is it. Now the processing gain, or PG, that is 2 to the power n, where 2 to the power n is the number of bits. The 2 to the power n is the number of 2 to n is the number of bits in the PN sequence. So 2 to the power n is basically the number of states. So why is the processing gain the number of states? Because you are either transmitting, say, if there are 4 hops, so you are either transmitting one symbol using 4 hops, or you are transmitting 4 symbols using, like, I got confused, sorry. So if you are having 4 states, so 2 to the power, like 2 bits PN sequence, so you have 4 states. So 2 to the power 2 is 4, so 4 states, you have 4 states. So what is the processing gain means? Processing gain means whatever is the maximum you can get as a efficient gain. So you are having what is the maximum utilization of this system you can make. If you want to transmit 4 symbols in 4 different tones, so you are transmitting to 4 users simultaneously in 4 different tones. So what is the processing gain? 4. If you are having 8 PN sequence states, that is 3 bits. So you can transmit 8 people together. So you will have a processing gain of 8. So you can get 8 means you can transmit to 8 people, multiplexing. So the processing gain will have 2 to the power n. So this will be number of okay, or okay. So here this is processing gain, and then there is another is power this probability of error. This probability of error is half e to the power minus eb by 2 n naught. However, I think the explanation is not included. If we encounter such an explanation, we can then derive later. So okay, now this is a slow FHSS demonstration. So consider a slow FHSS with MREFSK with number of bits per symbol is equal to 2. That is 2 symbol per hop. So MREFSK and number of bits per symbol is 2. So what is it? It is basically BFSK, binary FSK. Okay. Now, sorry, number of bits per symbol is 2. Sorry. It is 4. It's 4 FSK. So, and 2 symbols per hop. So there are one symbol has 2 bits and 2 symbols per hop. And PN sequence generated output with binary message, which is given as the message is using following PN sequence with k equal to 3. So the message is transmitted using following PKN sequence with k equal to 3. So 0, 0, 1, 1, 1, 0. So this 0, 0, 1, 1, 1, 0, these are all like PN sequences, one after another. So you are generating 3 bits at a time. 3 bits represent the states. So how many states are there? 8 states are there. Out of that, only 5 states are possible. So the PN sequence will rotate among these 5 states. So total 8 states are possible, but maybe 3 are forbidden. Anyways, so data message is having 2. So what is the solution here? The data message is having 2 bits per symbol. So possible combination of different frequencies used are 0, 0, 0, 1, 1, 0, 1, 1. Now here this F1, F2, F3, F4, these are the modulation frequencies. These are not your hopping frequencies. So 0, 0, because you are doing FSK, and this FSK is 1 minute. I have an urgent call, 1 minute. হ্যালো, হ্যাঁ, আরে এখন একটা মিটিংয়ে ছিলাম আসলে, তার জন্য কাজের রুমে বসে কাজ করছি, একটা মিটিং ছিল তার জন্য। হ্যাঁ হ্যাঁ হ্যাঁ, বাড়িতেই আছি। 8:30। 8:30 না, সরি, 8টা 8টা 8টা। আচ্ছা আচ্ছা আচ্ছা, ঠিক আছে। হ্যাঁ, কাল সকালে যাবো। হ্যাঁ, তুমি বিকেলে আসো, না তো সকালে আসতে চাইলে সকালেও আসতে পারো, তোমার ইচ্ছা। হুম। হ্যাঁ হ্যাঁ, কার্ড আমার কাছে আছে। হ্যাঁ। না না না, আর কিছু বলেনি। আমি ওই ইন্স্যুরেন্স ডেস্কে সব প্রেসক্রিপশন জমা দিয়ে দিয়েছি, তারপরে এবার যা হবে ভগবান জানে, দেখা যাবে। ওরা বলছে মানে ওই লোক এসেছিল, ওদের সবকিছু ডকুমেন্টস নিয়ে গেল, আর হসপিটাল থেকেও সব ডকুমেন্টস জমা করছে। হ্যাঁ হ্যাঁ, লোক এসেছে, একটা ডাক্তার পাঠায় ওরা। হুম, ঠিক আছে। হ্যাঁ, আজকে আজকে বিকেলে, তখন তুমি যখন বাইরে সোরেক্সোতে বসেছিলে বিকেলে তখন। না 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 না, আরে ছি ছি। হ্যাঁ হ্যাঁ, জানা নেই, কিছু জানা নেই। ওটা লাস্টেই জানা যাবে। ঠিক আছে। ওকে, হ্যাঁ, মিটিং এর পর আবার না হয় কল করছি, ঠিক আছে। হ্যাঁ। Yeah. Very sorry for the interruption. So 00011011. So this is a quadrature FSK. So two bits are taken together and mapped into one symbol. So one symbol means one tone, F1, F2, F3, F4. Now along with that you generate the hopping tone. This hopping tone will fluctuate wildly. Okay. Not as wildly because this is a slow FHS system, but still it will change. So that now here we are the relation between data sequence. So the data sequence is given as 0s 1 1 0 1 1 0 0 like that. So the data sequence is mapped into the PN sequence, and the data sequence is mapped into the PN sequence. So this logic is not this is mapped. Basically this logic we have to see later. So let's just assume this is mapped like this. Now here we are using three different groups of PN sequence, so three different hopping frequencies are used. So this is one hopping frequency, this PN sequence generates one hopping frequency, this PN sequence generates one hopping frequency, and this one generates another hopping frequency. So basically because there are like, yeah, so the three, so there will be three PNs now, three PN sequences they have written as FH1, FH6 and FH5, basically the decimal equivalents of these three PN sequences. So now the data symbol, see the data symbol now follow this graph. Data symbol is 0 1. So when data symbol is 0 1, it will transmit. What will be the frequency? Frequency will be 0 1 means it will follow the PN sequence 0 0 1. This PN sequence 0 0 1 means it is FH1, and this what is the symbol? The symbol is 0 1. So the FH value is FH1, and what is the frequency, modulation frequency value? The modulation frequency value is 0 1 means F2. So it is going at FH1 plus F2. This frequency is FH1 plus F2. Next is 1 0. 1 0 again will have 0 0 1. So FH1, again FH1 plus, but this time it is FH1 plus 1 0 is F3. So FH1 plus F3. So it is assumed that F1 greater than F2 greater than F3 greater than F4. So this F, you see, they are all above FH1, but 0 1 is at FH1 plus F2 level. This is at FH1 plus F3 level. Now you go to 1 1, you suddenly go to FH6. Now FH6 is pretty high, and 1 1 means it is F4. So this is not exact values. These are basically a concept. This is basically a conceptual map. So the exact frequency values may be different. Maybe F1 greater than F2 doesn't hold. It is just we are assuming like that. So F86 plus this frequency is F4 because we are transmitting 1 1. So F86 plus F4 means it is highest possible. So it is at the top. We are assuming that like FH1 greater than FH5 greater than f86, and we are assuming f1 greater than f2 greater than f3 greater, sorry, f1 less than f2 less than f3 less than f4. F4 is the highest. So whatever has the numeric suffix higher, that has the value higher. We are assuming like that. It may not be like that. Okay, we are assuming like that. So if fh, here we are using f86 plus f4, so it is literally the highest possible value, so it is at the top. Then f86 plus f2, like that. Then fh6 plus fh5 plus f3, then fh5 plus f1, like that. Okay, so on and so forth. Yeah, you can see fh plus 01 is fh plus f2, and 11 is fh plus f4. So this is the difference that is made. Okay. Now let's tackle the problem we have at hand. So let's read it again. F8 system with 6-stage LFS register, LFSR, generating the maximal length sequence. Each state of the register dictates a new center frequency within the hopping bandwidth. The desired hopping bandwidth is 81.9 MHz. The chip clock rate is 10 kHz. Assume MRE FSK modulation and data rate is 4 kbps. So minimum step size between center frequencies means what is the difference between the center frequencies of this hopping scheme. So minimum step size, how we solve that? So basically, let L be the number of shift register states and delta F be the frequency spacing and WS be the hopping bandwidth. So if there are L shift register states, so excluding 0000, all zeros, we usually exclude that, okay, because that is a dead state and we don't want to use that, because we cannot distinguish a meaningful 00000 information from something like a dead circuit is dead or there is no signal, something like that. So we usually discard 000, all zeros, as trivial. So it is 2 to the power L minus 1 states, and the frequency spacing between each of these tones should be such that if you take all the tones together along with their spacing, it should not exceed the hopping bandwidth. Is this point clear? So actually, unfortunately, I am at my home today, so I don't have my writing pad with me. So you have to bear with my horrible hand, means mouse drawing. So yeah, apologies in advance, but let's see what I can do. Okay. Yeah. So if you have something like this is your hopping bandwidth. So whatever hopping you have to do within this. Bear with me. H B W. Yeah. Yeah. So whatever you have to do within this hopping bandwidth. Now, this hopping bandwidth, you will have small tones within this hopping bandwidth, like one tone. Here is another tone. Like that, you will have multiple tones. Okay. Now, the spacing between them, let's say they are uniformly spaced. Usually they are uniformly spaced. So this is delta F. So this delta F times how many hops are there, that should not exceed the hopping bandwidth. So that leads us to hopping bandwidth is equal to 2 to the power L minus 1 times bandwidth times frequency spacing between hops. So this is pretty straightforward, I think. So you just solve, you just put, so 6 stage means 2 to the power 6, 64 states. One we will discard as trivial. So 63 states. 63 states, and the hopping bandwidth, that is the total allowed space for hopping, is 81.9 megahertz. So you divide 81.9 with 63, you will get 1.3 megahertz. So the correct answer is 1.3 megahertz. Yeah. Is this problem clear? Just answer in mic or in chat box, however you wish. Is this answer clear? Okay. So I have got an affirmative. Now, if m equal to 16, note that MREFSK is written. So MREFSK means it can be anything. It can be 2, it can be 6, it can be 10. So here it is written m equal to 16. So it is a 16 REFSK, means there are 4 steps, right? Sorry, not there are 4 steps, sorry. There are 4 bits per symbol. So there are 16 steps total. So 4 bits per symbol. So the number of chips in each data symbol is, now let's go to the solution. So we have to find the number of chips. Now the number of chips is basically the chip rate divided by the symbol rate. The number of chips per symbol. What they want is the basically the number of chips per symbol. So chips per symbol is chip rate by symbol rate. So now we have to determine, is this a fast fast frequency hopping or a slow frequency hopping? Because we have learned that symbol rate and hopping rate, whichever is maximum, will be your chip rate. That we have learned, right? So chip rate we know chip rate is equal to the maximum of hopping rate and symbol rate. So here hopping rate is chosen if it is a fast FH, and symbol rate is chosen if it is a slow FH. So here what is the hopping rate and what is the symbol rate? So the data rate is 4 kbps. So what is the symbol rate? How many bits per symbol? 4. So here question number, what is the question number? It is 1 part B. So here 1 part A, this is 1 part A, and this is 1 part B. So we know that chip rate is maximum of hopping rate and symbol rate. Now let's find out the symbol rate and hopping rate one by one. So symbol rate is bit rate divided by bits per symbol. So what is the bit rate? 4 kbps. So if you are sending 4 kilobyte bits, you are actually sending 4 kbps by bits per symbol. Bits per symbol is log oh, log 2 of the m. So it is 4 by log 2 of 16, which is 4. So 4 by 4, that is 1 kilo symbols per second or kilo samples per second. Now this is the symbol rate, and now we have to find the hopping rate. So to find out the hopping rate, we have to hopping rate. So how many hops are there? 63 hops, and hopping bandwidth, frequency hopping, register maximum, clock rate. So chip clock rate 10 kilohertz, symbols per sec. Okay. The hopping rate is 81.9, 10. So yeah, chips per symbol. Okay, okay. We don't need the hopping rate. Sorry, here we need only because it is chips per symbol. So we only need symbol rate. We don't need the hopping rate. So sorry. So here we have to find chips per symbol. So here we can just say that the chip rate. Okay, sorry, the chip rate is already given. We don't need the hopping rate because the chip rate is already given. The chip rate is directly given as 10 kilohertz. So we don't need to figure out what is the chip rate. The chip rate is 10 kilohertz. So here actually we don't need this formula because the chip rate is explicitly given. So symbol rate is this, and the chip rate is given to be 10 kilohertz. That is, this is 10 kilo chips per second. So this is kilo chips per second and this is kilo symbols per second. So what is the chips per symbol? The chips per symbol is the chips per symbol is chips per symbol is chip rate by symbol rate, which is 10k by 1k. So it is 10. It is simply 10. So the answer is 10. Okay, we didn't need the formula because the chip rate was explicitly given. Now processing gain in dB. So processing gain means whatever you are gaining from this operation. So here the processing gain we have seen is 2 to the power, usually 2 to the power n minus 1, because you are gaining that many only usually. So processing gain is 2 to the, because you are giving 2 to the power n minus 1 new hops. So it is 2 to the power n minus 1. Now in dB, so it is basically we have figured out that is 63. So in dB, pg dB is equal to 10 log 10 of 63. That is, let's open the calc. 10 into log 10. Oh, sorry. Log. Can someone just do 10 log 63? Okay, fine. 10 log 63. I think this will be quicker. So 17.99, which is 18. So 18 is 18 an option? Okay, so I think we are doing something wrong here. Okay, so the processing gain is defined a bit differently here. So here the processing gain is defined as the whatever the hopping you are doing, that bandwidth, and whatever bandwidth if you didn't hop. If you didn't hop, you would have just sent the data as 4 kbps. So the ratio of that. So it's not the ratio of the states. Here the hopping processing gain is defined as, now this processing gain, efficiency, these are parameters which are not uh, which are not very explicitly defined. These, okay, yeah, so these are so here it is defined as the bandwidth and the data rate. So your hopping bandwidth is 81.9. So basically now your FHSS system is occupying the entire 81.9 megahertz spectrum. So, and previously it would have occupied whatever spectrum is needed for 4 kbps. So it is 4000. So 4 kilohertz. So 81.9 megahertz over 4 kilohertz, that is 20,475. If you take decibels, it is 43.11. So the correct answer is 43.11. So please note this definition here. Processing gain is basically the, if the processing gain is asked in terms of states, then you can use 2 to the power n minus 1. But if explicitly hopping bandwidth and this data rate and all are given, then you have to use the processing gain for the hopping bandwidth, that is this. Okay, next, if now this one is if another system which is a FHSS BFSK system, which is used for transmitting binary data at a rate of 10 kbps. The unspread BFSK signal occupies a bandwidth of 20 kilohertz. Okay, so FHA, that unspread BFSK signal occupies a bandwidth of 20 kilohertz. That is fine. The received signal power is minus 10 dBm. A jammer which can produce a received power of at most minus 15 dBm, either as narrowband signal of 20 kilohertz or as a broadband signal occupying the full bandwidth of the FHSS system, is trying to jam the FHSS signal. The spreading factor of the FHSS BFSK system is 10. Assuming that a single-sided uh, assuming that a single-sided where where did I go? There's a full bandwidth. Assuming that a single-sided PFST of the AWGN of the channel is 10 to the power minus 11 watt per hertz, what is the receiver SNR under the various narrowband and broadband jamming scenarios? Now we have come to another concept which is called jamming. Okay, so jamming is another military or security application, primarily originating from military or security application. So one is spread spectrum is and jamming are often used in tandem. Now spread spectrum means you are talking to someone as if say you are in a completely English speaking audience. Let me give an analogy why how spread spectrum and jamming is used. So you are in a room full of English speaking audience. Now you have one friend who talks to you in your mother tongue. Say, what is your mother tongue? Let's say Hindi. So for example, so only you and another person, your friend, knows Hindi. Other people don't know Hindi, all are English speaking. So, if you want to communicate, you can communicate using Hindi, right? If you don't want other people to know what you and your friend are talking. Now, you are talking in Hindi, that is fine, but still in Hindi or in French, Russian, whatever language you use these days, because of globalization, we end up using English terminologies. We do not speak in a purely non-English language these days, no matter how hard we try. In whatever language we use, English always seeps in. So you might be afraid that whatever signal you are spreading across the room, some parts of it might be decoded by the English speaking crowd who otherwise cannot understand Hindi. Hmm. So, like if you say, "Arey kya scene hai yaar?" they might understand scene. Scene is an English word. So now what you do, you tell 10 people to start shouting in English, start singing, start blasting full volume music, do all that. So that whatever you are talking in Hindi, the people cannot even understand what you are talking, let alone the language. So if they can clear your noise and understand your word, then also they have to decode. So there you are introducing another barrier to the communication. Okay, so these are often used in jazz tandem. So here they are used in tandem. So I hope the analogy is clear. I took a bit of time explaining the analogy. But this now, what is the principle of jammer? How does jammer work? So jammer floods the entire bandwidth or a selected bandwidth with high power, so that your signal, your desired signal, will appear as noise. It will be totally out dominated. So here you can see that the jamming power, so the signal power is minus 10 dBm and the jammer power is minus 15 dBm. And so of course this jammer is not perfect, the signal power is still higher. Okay, so the signal power is 10 minus 10 dBm, but the band jammer power is lower, minus 15 dBm. Now the PSD of the narrowband jamming signal. So it is, first we are considering a narrowband jamming signal. So for a narrowband jamming signal, this minus 15 dBm, or in linear terms 3.16 into 10 to the power minus 5 watts, is spread across 20 kilohertz. It is either as a bandwidth of, either as a narrowband signal of 20 kilohertz or a broadband signal. So this is narrowband signal of 20 kilohertz. Okay, so this is there. Now so this power, this jammer power, will be distributed across the 20 kilohertz. So you end up with a 1.581 into 10 to the power minus 9 units of power for jamming. Now what is your SNR? SNR is basically wanted by unwanted. It is signal by noise, but it is also wanted by unwanted. Whatever power is wanted for your communication is your signal, whatever is unwanted is your noise. Now jamming is also a kind of noise, and AWGN is also another kind of noise. AWGN is a random noise, jamming is an intentional noise, a deterministic noise that has been sent to disrupt your communication. But you add them together as unwanted power and you take the EB by N naught. So what is EB? EB is basically the bit energy. So how do you get the bit energy? Basically this power divided by the bit rate. So with this power divided by the bit rate, so this power is sent in 1 second. So 10 to the power minus 4 watt is sent in 1 second, right? So in 1 second also, how many bits are sent? The 10 kbps, so 10,000 bits are sent. So bit energy is divided 10 to the power minus 4 divided by 10,000. So 10 to the power minus 8 bit energy. So the EB by N naught finally you get is dividing this bit energy by the jamming energy and the noise energy, and finally you get 7.98 or 8 dB. 7.98 dB. So yeah, you work out this. Now we come to the problem of the broadband jammer. Now what will happen in the broadband jammer? The broadband jammer will occupy the entire FHSS spectrum. So it's not the message spectrum, but the FHSS spectrum, which is much larger than the message spectrum, of course. That is the whole point of spread spectrum, that it will spread the information across a spectrum. Now okay, now the bandwidth of the spread signal. So what is the bandwidth of the spread signal? So it is 20 kilohertz by the spreading factor. So is the spreading factor given? The spreading factor is given to be 10. That is the frequency, whatever is the frequency of the original message bandwidth, it is multiplied by 10. So 20 kilohertz was the original unspread signal. So 200 kilohertz is your spread spectrum. So your spread spectrum is 200 kilohertz. So this jamming power, which is minus 15 dBm, is spread across 200 kilohertz. So now your PSD is 1.581 into 10 to the power minus 10. Previously the PSD was 1.581 into 10 to the power minus 9. So 10 times lesser PSD. Of course, because your bandwidth is getting spread by 10. So of course your noise power will reduce by 10. Sorry, jamming power will reduce by 10. So what is the EB by N naught now? The EB by N naught is basically the bit energy is same because the signal is same. So 10 to the power minus 8 divided by these two. So it is 15.9.94. Okay. So I hope this is clear. Next. Okay. Yeah. So now. Mm, okay. So you try this one. Question number 4. This also has a hop rate, and yeah, the radius. Okay, no, no, no. Let's leave question number 4. It is so. Okay. Write down one problem on my own. I am giving. So yeah, because these questions, whatever has been done, is mostly covered. So write down a problem that a PN sequence is generated using a four-stage linear feedback shift register. If the so let's write it down. Unnecessarily, I will not get this waste time. So yeah, a PN sequence in four-stage LFSR linear feedback shift register. Now the data rate is 40 kbps if the hopping bandwidth allowed is 100 kilohertz and AC. Frequency hopping. Okay, so here I have given you three questions. So a PN sequence FHSS system is generated using 4-stage LFSR. The data rate is 40 kbps. If the hopping bandwidth is allowed is 100 kilohertz, 4RE transmit and 4RE FSK is transmitted using this FHSS. Find the frequency spacing between hops. The what is the symbol rate, and if the chip rate clock is 10 kilohertz, what is the processing gain? Okay. So sorry, not 10 kilohertz. Let's make it 1 minute. Okay. Try this. I'll give you 5 minutes, and then we can come back and join. Okay. Sorry, then we can regroup and solve this together. Okay. Right. And if there is any data missing, you think, then you can assume any value for that and just solve the problem. If you think you need one particular data, say sampling rate, symbol rate, bit rate, whatever, you can assume and you can solve the question. Because I have given it from my mind, it might be the fact that I am missing one data. Okay. Just okay. Try this for at least 5 minutes. Okay, so where are you? At least frequency spacing. Frequency spacing is done. Okay, so what is the answer? Yeah, Mr. Suresh Kumar Patel, please. What's your query?
6.6 kilohertz.
Huh?
6.66 kilohertz
Six
frequency.
point. Okay,
Sir, delta
let's.
f is 6.66 kilohertz.
Okay, okay, okay. Yeah, I got you. 6.66. Let's check. So the hopping, basically, if there are 2 to the power L, so there are 4 stage. It is a 4 stage LFSR. So 2 to the power 4, we exclude 1. So 2 to the power 4 minus 1. So these are the number of states, number of hops possible. And each hop will have 100, basically the each hop will have some frequency spacing from the other, which is given by del f. Now this total will be 100k. So del f will be 100 by 15. So 100 by 15 is, I think, 6.66. Yeah, 6.66. So it is done. Okay. So this is 6.66 kHz. I hope the answer matches. Now what is the symbol rate? This is very easy. What is the symbol rate? Yeah, please go ahead.
Symbol rate is the 40k divided by 410k. 10k.
40k divided by
4 sir, 4 array is FSK na.
huh 4 array means
So 40k divided by 4.
yes, 40k divided by 4, that is 10k. 10k samples per second. So the symbol rate or baud rate is 40k divided by 4. It is pretty simple because 4 array FSK is there. So it is 10k. 10k symbols per second. Now what is the PG here? How do you get
Sir,
PG?
PG is the 100k divided by 40k. A hopping bandwidth is 40 kilohertz and data rate is 40k. So I think 100k divided by 40k. This is
Yeah.
3.97 dB.
Okay. Yeah. So it is 100k in dB. So it is 10 log 100k divided by 40k. So it is hopping in 100 kilohertz, but previously it used to be confined in 40 kilohertz. So it is 100k by 40k. What is the 10 log of that? That will be the answer. Yeah, that is done. Yeah, so now I will go to some more theory. So now this FHSS system is the carrier frequencies are chosen in accordance, and this is done. Yeah. So now we come to some disadvantages. We have and advantages, of course. First, we go through the advantages. One is that the processing gain PG is higher than that of DS3 system. Why is it higher? See, the in a DS3 system, so you are spreading the bits like previously you had 4 bits, now you are doing 12 bits. Okay, so if there is a, say you are transmitting 4 bits using a 12-bit PN sequence. So data is 4-bit, PN sequence is 12-bit. What will be the PG here? Just the ratio, tell me. 4-bit data you have, you are transmitting using 12 bits of PN sequence. So you are spreading it using 12-bit PN sequence. So what will be the PG here? The PG will be 3, 12 by 4, because you were sending 4 bits, now you are sending 12 bits. So your processing gain is 12 by 4, 3. But in the same case, you are having 4 bits. So 4 bits generates how many? 2 to the power 16. Sorry, 2 to the power 4. So 16. Let's reduce 1. So 15. So if you say that your frequency spacing, is the same as say the message bandwidth. So you are giving the frequency spacing between the hops to be the same as message bandwidth. So your hopping this processing gain now, because you have 15 states, so it will be 2 to the power L minus 1. So it is 2 to the power 4 minus 1, so 15. So you, since you have 15 hops, your processing gain will now be 15. It may not be, but in an ideal case it is 15. So previously you were getting a processing gain of 3, now you are getting a processing gain of 15. So it has a higher processing gain. Now, what does a higher processing gain? Why is it advantageous? You might say because we are occupying more bandwidth. But the processing gain allows us the freedom of multiplexing, because if there is more processing gain means we are getting more available slots than whatever was transmitted without spreading. So now we are getting more available slots, more users can be served simultaneously or something like that. So PG higher can be targeted, of course within a limit. The bandwidth has also to be limited, because of targeting very high PG. You cannot just say, hey, let's take this. I want very high PG, so I will take whatever bandwidth I want. Of course, your bandwidth is limited. Now, this another is the synchronization is not greatly dependent on the distance. So here your synchronization is basically frequency. So your frequency hopping synchronization you have to maintain, but you don't have to maintain bit level synchronization. In DS3 you had to maintain bit level synchronization. Now you have to maintain only frequency level synchronization. So a bit level synchronization, because say a normal communication system might have at least 1 Mbps. So 1 Mbps means every microsecond your bits have to be synchronized. Here if you're hopping, if you're using a very fast FHSS, of course this advantage does not hold good. But if you're using a slow FHSS, then what you're doing is you are getting more time. Okay, because your one tone might carry multiple symbols. So because you have to match the tone, it is much easier to match tone than to match bit. And you might get a purchase of more time if you are using a slower version of the FHSS. And second thing is, it is much easier to match frequency than it is to match bits. You try to match bits, there is some attenuation, there is some noise, it pushes the bit value. Because see, you are not transmitting 0 volt and 1 volt or plus 1 volt and minus 1 volt. You are transmitting a fuzzy value that is getting mapped at the receiver to 0, 1 or plus 1, minus 1. So this fuzzy value is susceptible to a threshold switching. So it is say 3 volts. There is a minus 0.7 volt. This 0 to 5. So minus 0.7 volt noise. Now you are getting 2.3 volts. So now you are getting 2.3. So 3 was there previously. Now minus 0.7 noise comes. So it is 2.3. Suddenly your 1 becomes 0. So it is much tougher to get just because of some stray noise. But here you have a fixed set of frequencies. You just have to, using phase lock loop, you have to just check whether these two frequencies are in lockstep. So it is a much easier task than doing bit level synchronization. And the serial search system with FHSS needs shorter time for acquisition. Now, what does this mean? This means that previously PN sequences were matched. Now you are matching a few tones. When you are matching PN sequences, it is much tougher, bit by bit matching. Now you are just matching tones. It is much easier to match tones. So the searching is easier. Is the advantages clear? Is any of the advantages dubious to according to you? If not, then we will go. Okay, so we will go to the issues or disadvantages. So one issue is that it is much more complicated. So here they have not written it well, but what is it means is basically it is more mathematically involved than a simple dot product. DS3 does not have any maths. You just have to tally the bits, whereas this does have math, and it needs more filters and all. There you are just tallying bits, so it is more mathematically involved. Okay. Uh, okay, and the second point is the repetition of the same, that it is high complexity. Next, okay, so they have basically written the same thing three times. So another issue, this is one issue, and another issue is that of FHSS is that because of the high processing gain, which is shown as an advantage, that can also be framed as a disadvantage because you are switching frequencies between a large bandwidth. So you are occupying a very large bandwidth compared to DS3. DS3 does not occupy that much bandwidth compared to this. So high bandwidth occupancy and complexity. These are the main problems with FHSS. And yeah, that is all for FHSS, and I have also given you a preview of jamming. And yeah, jamming we will do gradually along with the spread spectrum. So I don't think there is a dedicated week for jamming, or is there? CG, Kasami, Galoif, link budget, yeah, link budget and all will be mostly on jamming and this multi-user fading. Yeah, there will be content related jamming, but jamming will be mostly in like within, jamming will be incorporated within the problems or within the concepts, because jamming is not like, I don't think it will be dealt very separately, it will be within these topics only. So yeah, that will be all for frequency hopping spectrum. If you have any doubt, fire away. Okay, no doubts. Yeah, you have a doubt? Yeah, please go ahead.
सर डाउट नहीं है बस ये असाइनमेंट वन इन वन द क्वेश्चन नंबर 8 फर्स्ट पार्ट the bit rate given 0010 and the chip rate
Oh,
and bit rate PN sequence is not match sir any answer. I am doubt. I am little.
yeah, actually the solution first of all will be shared on 5th.
Sir,
And
I think there is some missing or something.
the thing is, see, 0010, right? That question.
uh,
0010 data, that question, right?
yes sir, 0010 and the
So
chip
if you
rate
match
is
your PN sequence, let's do it verbally only. You match your PN sequence. The PN sequence is 001101 110001. Is it correct?
yes sir.
00110110001. So this is your PN sequence. Now your data you spread three times. So 000 000 111 000. Okay. So each of the bits
Yes
will
sir.
be spread three times.
Four bits sir.
Yeah, each of the four
In
bits will be spread three times. Each of them will be spread three times. Zero will become zero zero
yes
zero.
sir.
Next zero will become again zero
Yes
zero
sir.
zero. Then 111 0
Mm.
0 0. Now, what you are doing is, see, when there are two different bits, you are getting zero, and when there are two same bits, you are getting one. So basically, it is an X
One.
NOR operation, right? Let's skip
Mm.
the bipolar. Let's say this is an X NOR operation. You understood that, right? Because minus 1 plus 1, that is
Yes
0
sir.
and 1, gives you 0, or plus 1 and minus 1 gives you 0, whereas 1 1
Yes.
and 1 1 and 0 0 gives you 1. So now you do XNOR between these 12 bits and these 12 bits. So first, starting from the left, 0 and 0, what is the XNOR? 1. Then 0 and 0, what is
One.
the XNOR? 1. 0 and 1, what is the XNOR? 0.
Zero.
Then 0 and 1, XNOR 0. 0 and 0, XNOR 1.
Mm.
0 and 1, XNOR 0. 1 and 1 XNOR 1, 1 and 1 XNOR 1, 1 and 0 XNOR 0, 0 and 0
Zero.
XNOR 1, 0 and 0 XNOR 1, 0 and 1 XNOR 0. So your final answer should come 1 1 0 0 1 0 1 1 0 1 1 0. I think that is an option here, right?
Sir,
That is the option 3, I think.
okay, sir.
You have understood, right?
Oh, yes, sir. Sir.
Okay. Okay, fine. Yeah. So that okay. Fine. Let's end this class now. You may leave the meeting. See you next week.